Today I want to talk to you about something about performance, something about web performance, and what we built, what we did wrong, and what we learned from it, maybe. And I'm Giulio, and I've studied here in Ca' Foscari. I did a master's degree in computer science here, and then I ran away to work abroad. And I like a bunch of things in computer science, like low-level stuff. For example, recently I'm doing like reverse engineering of silicon, and very high-level stuff like web technology. And I like to do performance work, which means taking systems that are slow and making them fast somehow. And recently I've been working for this company called Flux, and I'm a software engineer there. And I wanted to tell you a bit what I'm doing there. So Flux is this software that I'm showing here, which is a web-based tool to design printed circuit boards, like to put components together, connect them, and do stuff like simulation and then export it to manufacturing. And this is basically a very big web application built with technologies like TypeScript, where we have around 500,000 lines of TypeScript code, and we're using React and 3JS to draw the user interface of the application. And we're using other technologies like Firebase for the backend. And the complexity of the application has proven to be very high, because like we want to support documents which are huge with hundreds of components and connection between things, and the user needs to be able to click and drag everything and create a printed circuit board in this way. And so we have a bunch of challenges that come with building this product. We want to build giant documents with 10K electronic parts, each one with complex shapes associated to them. We support an advanced system in which each part can have rules assigned to them with inheritance and selectors. We have a pretty complex system that we need to support with a lot of dependencies. The entire document can be zoomed out and viewed at once, and the entire document needs to be interactive. You can click anywhere and move stuff around, like what you would do with like a very complicated CAD, computer design product. We have a bunch of algorithms running in the background. So we have not only your main thread that shows your application, but we have a simulator for the electronic things. We have DRC, which means checking the intersection between things if you did something wrong. So we have a lot of stuff running in the background. And we have a bunch of browsers limitation. Like we are running in the browser, so we are fighting against the limitations of the web. And for example, the limited amount of memory and the limited amount of processing that you can do in a JavaScript virtual machine. And all of these, we have the goal of being able to run this product on 60 FPS, even on medium level hardware on the browser, which proved to be really a challenge. And but when we started like a bunch of years ago, when we built the PCB editor for the first time, we had, for example, this specific document here, this specific PCB, which took around 4 or 5 minutes to open with your browser completely frozen. And sometimes it even crashed during loading, so it was not a great experience. And once it loaded, it was almost unusable because it was running at like 3 frames per second, which was really bad. And from there, we did a lot of work. And basically, we arrived in a state now in which we are able to display much more complicated stuff. For example, this board here, it's how the Tesla Roadster infotainment system works. And like basically you have a bunch of microcontrollers and CPUs. And now we're able to work with documents like these quite smoothly. We still have some rough edges, but we came a long way from that time in which everything was slow pretty much. And why is it lagging one behind? How did we do this? Like, what is the process that we keep internally? Well, the first thing that we do, it's what we call an incremental approach. We measure what is happening. We measure what are the things that are going slow. We dive deeper to find what is the cause of that slowdown or that crash, and then we optimize it. So we're not planning some big things and we are then rewriting everything every time, but we are doing it incrementally so that we are able to keep the product working and do improvements that can come day by day and not after giant projects, which is very important. And one of the things that we discovered this way is, for example, that on the browser we were having a very high memory usage, which doesn't seem like a big problem because, like, you might say, I have 8, 16, 32 gigs of RAM, who cares? But in the browser, it really matters, especially when your memory usage scales linearly with your complexity of the document. The reason why you want to care, it's because of this, because of auto memory crashes. Every time that, for example, on Chrome, you hit around 3-4 gigabytes of memory usage, your browser will kill your tab. Like, you can't catch it, you can't prevent it. On Safari, sometimes it's even like 300 megabytes of memory, especially on Safari iOS. And once you reach that limit, you just hang there for a few minutes, and then the browser will kill you. Which is something that actually a lot of people see in the wild. Like, for example, with the mobile app of Notion, it's very famous that sometimes it just, you load a very big document, it just crashes. And that's limitation of the browser that we had to work around. And another reason why you want to optimize memory usage is because of garbage collection. Because we all know that garbage collected languages are very cool, but the garbage collector takes some time. And if you're doing your memory management really, really, really wrong, like here there was garbage collector that took something like 10 seconds. And even if you are not in an extreme case like this, you can still end up in a situation in which at 20% of your function time, it's occupied doing garbage collection, and which means that if you are running, for example, it on a 60 frame per second loop, you will start feeling that garbage collector killing it. So you basically need to work like if you were doing a game engine. And the way that we solve this problem is by doing memory profiling, by using the Chrome profiler. It's that memory tab in the in Chrome inspector that maybe not too many people know about, that allows you to take a snapshot of the memory as it is right now and look inside of it and see what are all the different things inside, which allows you to find, for example, very big objects that are taking a lot of space. But sometimes it's not too useful because you just see a list with 58 million elements. I'm probably reading it wrong. And then you have to go through all of them. And you can't make much sense out of it. But still with that, we managed to do some optimizations. For example, this was a tiny change in the code in which we figured out that we were using UID wrongly. And by simplifying the code there, we basically had a 50% improvement on memory usage, which meant that things that previously just crashed now were entirely possible. And that was a big win that we had. And just that, as I said previously, the Chrome profiler doesn't really help you. It just allows you to take the data. But then it's very difficult to make sense out of it unless you have some extremely clear problems. Thankfully, there is this really cool software, this open source project by Meta called MemLab, which is an entire toolkit and library for managing memory snapshot, which allows you to basically load a memory snapshot that you saved, and you can perform analytics on it. For example, we used it to check how many megabytes of RAM were occupied by UIDs Should we optimize that? Should we avoid optimizing that? And with this, we were able to answer all those questions. One thing that we did, for example, was dividing all the memory usage by object type, which is something that Chrome doesn't allow you to use it, but we built our own scripts around it, with which we figured out that we had hundreds of megabytes used by internal React data structures, with which we basically figured out that we had a few specific things to optimize. And with this, we were able to, again, save hundreds of megabytes of memory and make other projects possible to load again. And if you're more interested about this topic, I did a bunch of talks about it, for example, at FOSDEM in Belgium some time ago. And I went in detail on how memory usage works. So if you're more interested if you're interested into the topic, just look that up. But we also did other things, like another methodology that we use for performance is frame profiling, which means that if you have a certain target of frame per second, like for example, you want to reach 60 FPS, it means that you have a specific amount of time in which everything has to be done on that frame, which is 15 milliseconds, for example. And everything has to fit there, because if something takes more, then the FPS will go down, because it will take more time, and the FPS are inversely proportional to the frame time. And with that, we were able to figure out a few things that need optimization. The Amdahl laws applies here, which means that you should optimize first the things that are taking the most time. And if you're not measuring, you're not able to make those kind of reasoning. Like, you're not able to say, that's the thing that is taking too much time, because a lot of time we thought that it was something, but actually it was something else entirely. And another thing that we optimized that way, that we figured out it was a problem, was raycasting, which means if you click with your mouse cursor somewhere on the document, what did you click? What should be selected? And the easiest way to solve this problem is to just for loop over everything and check if there is an intersection, like if something was clicked, which, as I see that most of you are computer science students, you know that probably there is a better way of doing that. Does anyone knows which algorithm data structure would you use to solve this problem? Assume 2D.
2D is R3, for example.
Okay.
Or some kind of binary search data where I can divide 4 coordinates.
Exactly. You use a data structure called quad tree or octrees, in which you have a binary partitioning of the space so that you can very quickly logarithmically find what you're looking for. And in particular, we're using this library called airbush, which uses a R tree inside, which means a tree of rectangles, because in our case, it's this way we are able to check the intersection between rectangle and rectangle, like it's a specific algorithm that is optimized for that. And with this, we were able to increment performance by a lot. Another thing that we optimized was text, because since we are on WebGL canvas, we had to implement text from scratch because we cannot use the one from the browser. And if you do it that naively by just using geometry, then you will basically be using 17 triangle and 51 vertices for each letter, which is incredibly wasteful. And normally the way that you optimize that is by using textures, like by using pre-computing all the fonts and just putting them as images. The problem is that if you do that, they're going to be extremely blurry. They're going to look very blocky unless you have a lot of very high resolution textures. And the way that we optimize that is by using a paper by Valve and the master thesis student of a guy from, I don't remember where, that explored this very cool technique called multi-channel signed instance functions, in which I won't go into too deep now. But the idea is that you represent for each glyph of your font a texture that represents the distance from the edge, which then allows you to accurately compute what is the border of that texture. And the good thing about this way of doing text rendering is that it ends up being extremely crisp, and you can do very easily effects like a blackout line around. And with this, we were able to draw like hundreds of thousands of characters on the screen without any problem and with having very, very fast performance. That's another thing. And but then that's only 2D. What if we have to do 3D text that has to be on a 3D, even on an extruded text that has depth? Well, that was another problem because we couldn't use the technique from before. So we looked into GPU instancing, which is a specific way to have the GPU draw thousands of millions of objects at the same time, which is pretty much the exact same thing that your average video game does to display particles or display a lot of trees in a specific area, and which is really fast to display the same object over and over. But here we don't have the same object. We have different characters. How do we solve that? The trick that we use is that every single font glyph, it's the same object, just that then we encode the actual positions of the vertices on a texture, and then we use some GPU magic to get the information back from that texture and apply it as a 3D position. We reached this level of complication just to draw text, and which allows us to gain a few FPS, but it was cool. And this is a bit of a segue into my next topic. And this is a bit of a demo of what we can achieve with this technique, that we can have a lot of 3D text with pretty good performance. This is all running on the browser. And segue to my next topic, which is, okay, we did a lot of cool trickery and cool techniques. And did they improve the quality and the performance of the system? Well, most of them did. Some of them gave a marginal improvement, like, for example, the last one that I showed you. Because, again, the Amdahl laws applies. You can make faster only by that percentage that entire thing is taking time. So if you have something that is 10% of your system, you can only make your system 10% faster if you optimize that as much as possible. And so it became clear that we also had some other deeper problems in our code that we had to fix. And the question that, and everything that we did so far was incremental, was one small thing after the other. So the question that we had is, can we really make a system fast incrementally? Is it really possible to take something that is slow and make it fast again just by changing it a tiny bit at a time? Yes and no. Because in software for performance, architecture is really important, which means how your data is stored, how your data is transformed, and how your data is moved around. And sometimes those architecture are so deeply rooted in your code that if you want to optimize that, basically means a rewrite. And in our case, our architecture was really, really bad, because we had that rendering, the rendering part had too many responsibilities, and the rendering part was deciding too much stuff, whereas the business logic was a bit detached and was extremely slow. And this brought to a lot of problems, because we only tried to make it fast by touching rendering, those adding a lot of responsibility to rendering, which, what happens if we add more features? What happens when we added the export, overlap detection, filling, and all stuff like that? We ended up with a lot of duplicated code, because if rendering has too much responsibilities, then all those responsibilities had to be replicated in all the other CM systems as well. And since we wanted to build those other systems as quickly as possible, it was very difficult to keep them in sync. It will happen that we would basically have two systems that gave completely different outputs, because to make them fast, we re-implemented everything every time. And this showed a lot, because we were trying to move everything to the GPU, just that it's very difficult to make sure that what the GPU produces is the same thing that an export algorithm does. So this was a big problem for us, because like we ended up with implementation that caused bugs against each other. And this also had the problem that every time that we wanted to implement an interaction like this, for example, this drag interaction in which you can move around the wire, all of that interaction was basically manipulating the GPU data directly for performance, because the business logic was too slow. So we had to re-implement the business logic again in rendering, because that was the only way to make it real time. And then we had to apply those changes back, which sometimes will come in a different way, because the business logic was using different code. And so we had no way of doing those transient states, which was really hard to get around. And another problem that we had was a bad data subscription model. In React and in web development, you have those patterns in which you have a data store, and you can put data into it, and then you can subscribe to it, which means get notification, gets a function called every time that something changes. Just that you don't want if you have a lot of changes, you don't want thousands of functions to be called every time that something changes. Otherwise, it will be like if you need to redraw everything every time, it will be incredibly wasteful. So the way that normally you solve this problem is by using selectors, which means having a function that, given the entire state, selects a small part of the states that is the one that you need. And that way you reduce the load a lot, and ideally you just update when needed. The problem is that those selectors, we made them more granular to be able to catch more granular changes. And then the selector became slow as well. So we ended up with, again, the same problem, that every time that you changes something, hundreds of thousands of functions would fire to diff the state versus the previous one. So it was all slow again. And this is a problem that normally it's done for convenience, because a lot of things in React work like this in that specific framework. And a lot of web applications don't have a lot of data, so they don't really care about having this problem. We care, because we have documents which are hundreds of megabytes, and this was very slow. And the way that we solve this is by building our own data store model, in which every part of the store can have a function attached to it, so that that way we know precisely who wants to know when something specifically changes, and we can do that in O1 instead of ON with growing the size of the state. And another problem that we face is that we built everything with React by using a React component for every single thing that you see on screen, which proved to be incredibly expensive. As I showed previously, it was using gigabytes of memory, and simply we were working around an abstraction that was supposed to help us, but ended up just getting in the way, because we were doing something real time, but React is not built for a lot of changes to be done in real time. So we had to patch around the abstraction, creating some horrible monsters. And the problem is that we were constantly gaslighting ourselves into saying, yeah, but that's the proper way to do things with React, not figuring out that actually we were shooting ourselves in the foot multiple times with this. And it's very hard to convince developers of those things, especially when you work on a code base for over 4 years. So that was another problem that we had, and now we're using a solution that is ideally better, which I call the shape strategy, which means that previously our system was reasoning about the data in a too high level, and we put another system in between, which makes the system reason about stuff in a bit lower level. Instead of thinking about vias, traces, and paths, which are all things that electronic uses, we are reasoning about shapes. We're not reasoning about a true hole path with a hole offset and solder mask, but we are reasoning about a rectangle with a circle inside of it. And that's much simpler. And that's a thing that all the system can reason much better about, instead of having to interpret everything every time. So we basically did a giant refactor. We are still doing it, in which we are moving this responsibility away. And so that also the shapes can provide a standard library, such as what is the bounding box of the shape, or are two shape overlapping. Previously, we were re-implementing all that stuff over and over because different people did those systems. And when you end up with 500,000 lines of code, people forget that utility function exists, because maybe the utility function is deep 50 folders deep in the utils.ts or something, or hidden in a code file somewhere. And people don't have time to talk to each other about this kind of things. So no more guessing and no more implementing, which is a very good thing, I would say. And we ended up with this system now in which all the shapes go through a dispatcher, which automatically gives all the shapes to very specialized things, which are able to draw stuff like circles, rectangles, octagons, and stuff like that very fast. So the rendering part now, it's finally just doing rendering, and it's not understanding what the business logic should be by abstracting this thing this way. And so this way we can reduce subscriptions, which are problematic, and we can group similar things into super components, which is this idea that instead of having thousands of components rendering everything, you just have a few components that render everything at once. Exactly. And so what we learn from this is that changing architecture is hard. Like if you have a system that is a bit dysfunctional and it's not performant enough, you want to move towards something different. But that's incredibly hard because sometimes when you are at the beginning, you say, oh, we will have this and this and this feature, which is a thing that rarely materializes, and business needs change a lot. So maybe you optimize for those features and you keep saying, yes, but in the future we want to do that. And that's a thing that eventually brings you to optimizing stuff you don't have and you will never have. And you build system with the wrong ideas. So the more that you keep it simple, the better. Another thing is that, well, you shouldn't write stuff, because we tried it. And there are like one type of rewrite, the one that fails. And every time that you start with the assumption of rewriting something, you're basically ignoring the fact that a lot of people suffer through it. And there is a reason why they suffer through it. And you thinking that you won't suffer through it, it's a bit of an hubris act. And rewriting it rarely works. And another thing that I learned is that people are very hard to convince. Like if you're working with 10 other engineers and all of them worked in that code base for like 5 years, all those people will reason about what you say only in the terms of your code base. Like if you have a specific system that works in a certain way, all the people will be like, yeah, but how will the system works? Well, that system, we don't need it. We're trying to remove it. But how can we do it without it? People are so convinced that that system that you have is the only possible, that moving them away from it is going to be extremely hard. And if you have like, this is another problem that I'm facing, and it's that I'm trying to refactor this thing, trying to reason in a lower level about stuff, and getting people on board on it with it is extremely hard, because sometimes they will tell you, oh yeah, that's a very good idea, let's do it. But then when it comes to actually use the utilities and use the framework and use the system, they won't, because you need to constantly pair with them and show them that you build the code to solve their problems. They can use the code. It's not your thing that you're doing. It's the thing that everyone should be doing. And that's an incredible thing to do. It's an incredibly hard thing to do. So we have this thing that we say internally, which is chasing the North Star, which means thinking about how things could be in the future. And instead of just planning around how to reach that now, it's more like of a continuous effort of moving towards what's the star that is bringing you to salvation. And which means that you can think of a better architecture, what is the architecture that it could look like, and continuously readjust. And reach it one small change at a time. One thing that we do is that since it's very hard to get approval for refactoring stuff from product, like if you tell the product that I want to refactor this, they will tell you, no, please build a feature. But you can put more refactors into features and into bug fixes. You can Trojan horse those things by masking them as bug fixes. And while you're doing this thing of you yourself trying to move towards the better destination, you need to keep pushing people to adopt it and continuously pair with them and tell them, hey, do you want to use this utility that I built? Do you want to use this new architecture? Because otherwise you would forget about it. And that's normal. And that's sometimes one person told me that leading is repeating, which I think that here applies a lot. And so yeah, that's what I was going to talk about.